Section 2.4 is on scatterplots, correlation, and regression, which would just be another way that we can turn around and display our data. A scatterplot and correlation. First things first, the correlation is the values of one variable associated with the values of the other variable. And those values then are referred to as being paired variables or bivariate. A linear correlation is a correlation between two variables where the plotted points of paired data result in a pattern that can be approximated by a straight line. And it's usually the easiest when it is indeed a straight line. Something similar to this graph here that I just drew, although that one isn't going to be as nice of a straight line or as nice of a correlation, but it does follow the overall trend of a line. A scatter plot like the one that I just drew here, or scatter diagram, is a plot of paired x, y qualitative data with a horizontal x-axis and a vertical y-axis. The horizontal axis is used for the x variable and the vertical axis as the y variable. And one very, very, very important topic when it comes to correlation is that correlation does not imply causality. Or another way to refer to it is the association. Does not imply causality or causation. Both of those mean the same idea. Meaning that if two variables are correlated, they have some type of association, which is what allows us to be able to use a linear correlation and to be able to draw a scatter plot and then eventually a line of best fit through this data. Right? But based upon that, though, that does not necessarily mean that those variables are caused by each other. A very important topic to note. So, for example of a scatter plot, the data1 biodata dataset includes waist circumferences in centimeters and arm circumferences in centimeters of randomly selected adult subjects. The scatter plot down here of the paired waist and arm circumference measurements is shown below. The points show a pattern of increasing values from left to right and from bottom to top. This suggests that there is a correlation or relationship between waist circumferences and arm circumferences, and due to the way that it increases from left to right, increases from left to right, and increases from the bottom to the top. This would be a positive correlation. Now, how strong this correlation is, we would need a specific calculation to get that correlation coefficient to find out what that actually is. But the whole idea of it, though, is it's positive since both variables increase from left to right, or up to bottom to top. A second example, using that same body one data set body data, including now the weights in kilograms and pulse rates in beats per minute of randomly selected adult subjects. This scatter plot of the paired weight pulse rate measurements is shown here. The points do not show any obvious pattern, and this lack of appearance suggests that there is no correlation or relationship between weights and pulse rates. As we could see, these points are all over the place. You wouldn't really be able to approximate a line too well. A correlation coefficient for something like this would be very close to zero. Again, to note that there is no correlation here. No relationship. No association. That type of spiel. And the linear correlation coefficient, denoted by a lowercase r, measures the strength of the linear association between two variables. And it's always between -1 and +1. And a value of +1 or -1 is a perfect positive or perfect negative correlation. So this one being positive, and this other one being negative, based on if it's +1 or -1. If it's close to -1 or +1, then the correlation is strong. Again, negative and positive. And if it's close to 0, there's a weak or no correlation. I should also probably note it might be nonlinear. Which means it's a good idea to actually look at the scatter plot before actually trying to identify relationships, due to the fact that nonlinear data also would have a correlation coefficient close to 0, especially if there's a lot of it. My next example here, concerning this data from the dataset 7 foot in height dataset, from the accompanying scatter plot of the paired data, it isn't very clear whether there is a linear correlation between these data points. Right? There's only a total of 5 data points. And it looks to be increasing from left to right and from bottom to top. We have a point all the way out here doing its own thing, and then this one here kind of almost starts to decrease a little bit. So you really can't tell that much if it's a linear correlation. And a stat disk display of the results shows that the linear correlation coefficient has a value of about 0.5912691. So this being a relatively, this would be a moderate relationship based upon that correlation coefficient. But even despite that, you can't really see a clear line being drawn between these points. The data 7 set foot and height data set, we could also use the shoe print lengths and heights from all of the 40 subjects listed. So we get this scatter plot down here, and the menu tab results shown up here. The scatter plot does now show a distinctive pattern, instead of having points scattered about willy-nilly. Also, we see that the value of the correlation coefficient down over here is 0.813, which shows that there is a linear correlation between shoe print lengths and heights. This one now is a lot stronger. And because from left to right it increases, and it increases from bottom to top, this is going to be a positive linear relationship. So this is a strong positive linear relationship. And as such, when we eventually do form the line of best fit, it will have a positive slope, and which is a good thing. Well, it doesn't matter if it's positive or negative per se, but as long as it has a correlation coefficient indicating that we have indeed a linear relationship. And speaking of linear regression, we use this when we want to establish that linear relationship with a regression line, or line of best fit, or least squares line, or some variation thereof. That's the straight line that best fits the scatter plot of data. And the reason why best is in quotation marks is because this is approximated from the data. And there's a special formula that does so. But the equation of this line of best fit, this is y hat is equal to b sub 0 plus b sub 1 x. Alright, b sub 0 is our slope of this regression line. B sub 1 is the slope of our regression line. B sub 1 is the slope of our regression line, and b sub 0 is the y-intercept. Alright, so using this graph that we've shown down here, we see the line of best fit for the scatter plot is this y hat is equal to 80.9 plus 3.22x, which we could see based upon the stat disk output down here, the last two entries. It also might be useful sometimes to write this out with what the variables actually mean, as opposed to just the equation, since sometimes by just looking at the equation, unless you know what the variables mean, you won't know where you put certain values. So here height, which is the y variable, is equal to 80.9 plus 3.22 times the shoe print length, which is the x variable. Thank you.